So thank you very much for that introduction. It's very nice. Oh, hold on. Is this the wrong screen? Okay, maybe you can you see now? Okay.
Yeah.
Thank you. Yeah, thanks for the invitation to speak. It's a real pleasure. So yeah, I'm going to talk about what we can learn about the galactic structure. That's the structure of the Milky Way's stellar populations from cosmological hydrodynamical simulations. And yeah, obviously the Milky Way is just one spiral galaxy, but it's the only spiral galaxy for which we have detailed star-by-star information for, which gives us a unique window into galaxy evolution and near-field cosmology. And in particular, if we want to use the stellar populations of the Milky Way as kind of fossils in this practice of galactic archaeology to reproduce or to constrain rather the evolution and formation processes that has shaped these populations. It's a great opportunity to do that, especially these days, where we've been gathering so much of this kind of information through surveys like Gaia, which has given us photometry and astrometry for billions of stars in our quadrant of the galaxy. And this will, be enhanced even further with future Gaia data releases and other surveys like the LSST and the Vera Rubin Observatory. And on top of that information, we have a range of spectroscopic surveys. At the moment, we have Apogee, Gaia-ESO, and we will have soon WEAVE and Foremost, which will give us accurate radial velocities as well as chemical abundance information. And for a subset of those stars, there are surveys like astroseismological surveys like K2, TESS, and Plato that will give us accurate ages for a subset of those. So we really end up with a lot of very high dimensional accurate information for many, many stars in our galaxy. So we really are living in this age of discovery for the Milky Way and its stellar structure. And in this talk in particular, as Federico mentioned, I'm going to focus on the Milky Way's double disk or thin and thick disk structure and stellar halo as well, to understand what we can learn about that. So as just a bit of a background, we've known for quite a while from this study of Gilmore and Reed in the 80s that through number counts of stars above and below the plane, that it can be this distribution can be well decomposed by two exponentials with different scale heights. So we have a thin component with a shorter scale height known as the thin disk, and a thicker component here with a larger scale height, which was known as the thick disk. And in addition to that, we've also known for a while that there seem to be two distinct chemical tracks in the stellar populations around the solar neighborhood. So this plot here shows you the magnesium over iron as a function of iron abundance. And as we enrich our stellar populations from left to right with type 2 supernovae, and then type 1As kick in and move us towards the lower right of this diagram, if this were just a single one-zone model, we might expect a single chemical track. But what we actually observe at certain metallicities is that there is a bimodal distribution in the alpha over iron distribution. So that indicates something a bit more complex. And maybe this is the thin disk and thick disk in the chemical space. And more recently, we've had data thanks to surveys like Apogee has managed to map this kind of structure across the disk. So here we see the same plane. So this is alpha over iron again versus iron abundance, but this time split over different regions of the disk. So from left, we have the inner disk. As we move to the right, we move towards the outer disk. And the lower row here is in plane, and the upper row is slightly above or slightly out of the galactic plane. And so you can see, of course, around the solar neighborhood, this dichotomous feature is still visible. And interestingly, we can look at the structure and see that if we try to map directly this high alpha thick disk to the geometrical thick disk, and the same with the low alpha sequence, we do not find quite a simple mapping between these two definitions. So actually, is something that looks more like this. So if we were to look at the high alpha sequence and call that a thick disk, then this, yes, indeed is quite vertically extended, but it's also quite compact, it's radially compact. Whereas if we look at the low alpha sequence, this actually extends quite far out into the galaxy, and it also begins to dominate at certain radii once you get beyond a certain radius. So the scale height actually increases as we go out to it for this component. So it's quite a complex mapping between this geometrical and chemical definition of a thin and thick disk. And then more recently, Gaia-DR2 came out and mapped this in more detail, and it also made several discoveries, really revolutionary discoveries. But today I'm going to focus on this one discovery, which is about the Gaia-Enceladus-Sausage merger, which is now sort of widely known as the Milky Way's last significant merger. Now we can also look at the chemical properties of this and the dynamical properties, but this plot shows the plot from Helmy, 2018. In the black points, you see the familiar thick disk and thin disk in this dichotomous feature, and the blue points show the chemical distribution for what is thought to be the remnant of this merger. And that has different chemical properties. Now, this plot on the right shows you kinematic information. So this is from, actually the original plot was from Belukharov in 2018, but I show you here a reproduced version from Fatai 2019, which shows you the tangential velocity on the y-axis as a function of the radial velocity. And what you see is that there's a kind of, well, of stars of a kind of intermediate metallicity range around our position of the galaxy. And this blob here is probably the thick disk, has some rotational component, but there's also a kind of distinct elongated component, this anisotropic, radially anisotropic component, which was referred to as the sausage because of its shape. And so these two things are thought to be very similar, and I will call it therefore the Gaia-Enceladus-Sausage merger, just to bridge these two works. Now, since then, Belukharov, a couple of years ago, did a careful decomposition of the velocity distribution in the tangential direction, using a lot of different surveys to piece together the velocity distribution. And he decomposed it into three components. You have the thin, the rotationally dominant thin disk, there's the thick disk, and then there's another kind of distribution here with a peak that's just above zero. So it's mild, very mildly prograde rotation. And this was dubbed the splash, and this is thought to be perhaps the proto-galaxy or the proto-disk that had been kinematically heated by the merger itself, and as a result lost a bunch of its rotation. And that's the splash component. So that leads me to the two of the main questions I'd like to focus on in this talk, which is what are the properties of this Gaia-Enceladus merger, the progenitor itself, and what is its role in the formation of the thick disk and the halo, and also the thin thick disk dichotomy here. So to try to understand this, I'll use cosmological simulations to see what insights we can get. And I just wanted to show this slide to highlight that these days we really have there's several groups around the world that can produce realistic looking disk galaxies using cosmological simulations. It used to be more than a decade ago that this was pretty difficult to do. And in fact, not many people at all, I think at that point, managed to reproduce an extended disk component with a spiral, barred spiral morphology. But thanks to improvements in prescriptions for stellar feedback mainly, but also in the numerical schemes and resolution, now we have all these different kinds of simulations. And I'm going to focus on results from the Eureka simulation suite, which is simulations that I'm most involved with. So this is just a movie from one of these simulations, and they start from well-defined initial conditions set by the cosmic microwave background at very high redshift. And then we put in our prescriptions for gravity, star formation, supernova feedback. We also have black hole accretion. And then we let this go and we focus on a galaxy of interest. In this case, a Milky Way-like galaxy that you can see in dark matter, gas, and right, these panels. Here you see an infalling group of galaxies that actually one of those galaxies is what we would call a Gaia-Enceladus analog, which I'll talk about in a moment. But of course, the real strength of all this is that we can evolve all of this to redshift 0 and try to infer the structures that Gaia sees. So looking into our simulations, we have about 40 of these simulations. And we searched for features like this. So this is just the Gaia-Sausage again in kinematic space. And we found a range of different types. So in this top right montage here, I'm just showing you the kinds of features that we can get in this space. So we have a range of cases, some which don't have this kind of elongated anisotropic feature at all. Some that you may consider, okay, it looks a little bit elongated, but we cannot really distinguish clearly something separate from the rest of the distribution. And on the left, we have clear cases that have this kind of rotating thick disk component with an elongated sausage. And we have about 10 of these. And if you look at the formation histories of the ones like this, which have clear sausages, this plot in the bottom right shows you the matter accretion of the dark matter as a function of time. And so this red curve shows you those galaxies that have that feature, and the blue ones show you the ones that don't. So you have a kind of earlier assembly history of the ones that have the Gaia sausage. And this early accretion history seems to be dominated by a single object. In some cases, you get a companion object as well. But mainly there's a dominant accretion event with a mass between about 10 to the 8 and 10 to the 9 solar masses. And there's also a wide range of possible accretion times that we found from our simulations. So between 6 and 11 gig years ago. So we can't get super strict constraints on the progenitor from this analysis alone. Okay, so I just want to focus on one particular example just to demonstrate how it might impact, how we think it might have impacted the young Milky Way. So first of all of the progenitors that we found are always gas rich, and they always make a starburst as they come in, contributing anything from up to half of the gas that takes part in this starburst. And this is the star formation history for one of these galaxies. In the black is everything. And the purple here is the Gaia-Enceladus progenitor that we identified, multiplied by a factor of 10 in this plot, so we can see it. And you can see when it merges here at about 9 gig years ago, there's a big peak in star formation. That's the starburst. So what I'm going to do for most of the rest of this talk is distinguish the stars that were formed in this burst and call this the starburst material. And everything in red is stars that are formed in the protogalaxy before this merger took place. So I'm going to differentiate these two populations. So how do they look in chemical space? So this shows you the alpha over ion versus Fe over H. The left panel shows you the inner disk, and the right, the outer disk. I've also color-coded the thin disk here, which is this region, and you can see this is distinct from these other populations. The starburst population occupies this region here, fairly narrow region of this space, which we would also expect. It's kind of like thick disk territory. And the protogalaxy itself also overlaps significantly with that population, but it stretches further back into more metal poor territory, alpha rich territory as well. And if we further divide this protogalaxy material into a protohalo, which is the very low angular momentum protogalaxy stars, essentially, this goes even further back. And it seems like all of this kind of material is fairly smoothly connected. So between the thick disk and the stellar halo. Now, there's a very similar story in the outer disk, except for this metal poor protohalo material is not really present. And this to me indicates that the metal poor stars are heated more by prior mergers, which are then able to actually reach these larger radii and have a larger extent than the metal rich protohalo. Okay, and what about the kinematics? So to illustrate this and quantify this a bit, this shows you the circularity distribution of stars in these different components, where 1 here indicates a perfectly circular orbit on a prograde direction. 0 is a perfectly radial orbit, and -1 is a perfectly circular retrograde orbit. Now, in this case, the Gaia-Enceladus progenitor material clusters around this 0, so it's not really rotating. Maybe it's mildly prograde, but it's what we expect roughly from a radial merger. The starburst material is where you would expect the thick disk to be. It has predominantly prograde rotation, but it's not a thin disk material, which would be around a 1. And likewise for the protogalaxy, which is this thick red line. Now, this thin red line shows you the protogalaxy material just before the merger. So you can see here it's actually more rotationally dominant than it is at redshift 0. And this can be illustrated here on the right with this before and after picture of the stars. So if we looked at the stars from edge on before the merger took place, we would see this. So it's reasonably flat, reasonably thin. And then afterwards, this puffs out quite a bit. So this is just illustrating the potential kinematic heating effect that the Jez progenitor had on the protogalaxy. Now, combining these things, we can look at the rotation velocity as a function of metallicity. And we see here that both the starburst and the protogalaxy material exhibit this positive gradient, which we would also expect for the thick disk. And we interpret this as essentially the starburst material that formed mixed quite quickly to occupy a relatively narrow region of chemical space, and it dissipated the energy that it got during the starburst to form this compact rotating thick disk, which actually sort of marks the end of the chemical sequence of the protogalaxy, which was also heated partially into this halo or this splash population to connect to the halo. So we would conclude by inferring that essentially this indicates that the thick disk connects smoothly to the halo, and we have a dual origin of the thick disk from protogalaxy material plus the starburst material that the Jez caused. So how can we constrain the properties of the Jez from these kinds of observables? Well, one thing we could try to do is look at the number of splash stars as a fraction of the total stars. So if we try to quantify the fraction of splash stars that we get, if we think that the mass of the progenitor, for example, will cause more damage to the disk and increase the fraction of splash stars, we do see in the simulation suite that we have a trend, albeit with quite a bit of scatter, that sort of bears out that expectation where more massive progenitors would increase the fraction of stars on counter-rotating orbits or splash orbits. How about dating the merger? So on the right-hand side here, if we take these counter-rotating splash stars and we diagnose, we look at their age distribution and maybe look at the lower quartile of this distribution just to as a proxy for when the merger finished. And we divide this by the true merger time of the simulations and take the log, such that anything around 0 is basically a perfect prediction for the merger time. We can see that this is where our simulations lie, and most of these points lie within 0.1 dex of the true merger time. So that's about within 20–25% of the merger time. So maybe the age, if we could get ages for counter-rotating stars, we can maybe date the age of this last major merger. And so we can sort of already play this game in a way. So on the left, I'm here showing you the velocity, the tangential velocity. It's a function of age of the stars, binned in this 2D histogram. And here, this red line marks the merger in this particular case, the Gaia-Enceladus merger. Everything to the left of this line, you can see that there was a big, this counter-rotating stars is really, dominates this. Maybe not dominate, but there's quite a lot of them here. And then there's not really that much after this merger time. So it does seem that this might be a good predictor. And if we look at the actual Gaia data and play the same game, and you can sort of draw this line around here where the fraction of counter-rotating stars really dwindles. And that seems to indicate that the merger may have taken place between 9 and 10 gig years ago. Right. So there's also the question of how did this merger actually start bar formation or play a part in bar formation, because the bar is also thought to have formed around about the same epoch. And we also found this interesting case, actually the same galaxy I've been talking about for most of the talk, which does form a bar very similar to the one we have in the Milky Way in terms of morphology. So this is what it looks like face on. And edge on, you can see this X-shaped distribution in the middle, which is this boxy bulge feature that we know the Milky Way has. And if we look at the evolution of this bar in terms of this A2 parameter, this is just the Fourier amplitude of the m equals 2 symmetric component in the inner part of the galaxy, you can see that it grows, it's pretty low down here, and it only really goes to the level where we would call it a strong bar at around about 9 gig years ago. And this is exactly the point where the merger comes in. And then it grows to this point, and then it buckles a few gig years later and forms the boxy bulge. So if this is the case, that the Gaia-Enceladus-Sausage merger actually instigated bar formation in the early galaxy, our simulations seem to indicate that it would prefer a relatively low mass merger, because what happens is, if you look at the kinematics of the bulge stars, this is the velocity and this is the velocity dispersion as a function of the galactic longitude, so the line of sight that you're looking at. And you can compare these distributions for different metallicity populations with data, and the data are the points here from the Argos survey. Only the low mass, relatively low mass JS progenitor can match all of these features relatively well. And if it's too massive, it just heats up the older metal poorer population too much, and it has no rotation, and it doesn't really match the observations very well. So I think this is a potentially interesting potential insight on this. Okay, so the last thing I want to touch on is this thin and thick disk dichotomy. So what I talked about mostly was what was happening in this thick disk halo regime up here, but I didn't really discuss this dichotomous feature for which you need this low alpha sequence or at this kind of metallicity range where there's a bimodality. So I just recently we managed to tag ages for many of these stars from Apogee using a machine learning method, this bingo Bayesian neural network technique. And this is what this looks like if we color these points by age. And actually what we find here is that these two features, the thick disk and the thin disk, are actually fairly well separated in ages. So everything below about 8 gig years in age pretty much belongs to this thin disk component, and everything above that is more or less pretty much belongs to this thick disk component. So they seem to follow on from one another in this particular picture. So looking into our simulations, we found, we tried to reproduce this sort of qualitative feature. And we did find a case that did match this. And it gave us some insight into a fairly peculiar formation history of this bimodality. So firstly, if we take the first snapshot here, the first moment in this buildup, we have this violent early phase where there's a gas-rich merger, like the Gaia-Enceladus, for example, and that creates this burst of star formation. You can see in this middle panel here, this is the red line in the inner galaxy, peak in star formation, creates our high alpha sequence in the chemical abundance plane. These red lines are age contours, so you can see roughly what ages these stars are. Then we move to this point here, which is 2 gig years later, where the gas disk has grown out quickly. And now we're looking at chemical abundance space in the solar neighborhood. So it's grown this high alpha part out into the solar neighborhood here. And now we have a peak in star formation around the solar neighborhood at 8 kiloparsecs away. But then there's a drop in star formation because gas accretion is cut off for some reason around this galaxy. And at this point here in this image labeled 2, you can see that the gas disk is actually smaller than it was in this image here. So the disk has actually shrunk because gas accretion has stopped fueling the edges, and it's shrunk down until the galaxy accretes a gas-rich metal-poor minor merger that you can see in this image as well. And that dilutes the metallicity, the gas metallicity around the edges of the disk. And we get brought back to here in this diagram, in the alpha abundance diagram. Then once this gas settles, star formation is reinvigorated at this late time here. The disk galaxy grows out again and forms the low alpha sequence. And in this way, we can get this bimodality at this metallicity of about 0.2 or so in this case. Now, interestingly, I just want to point out this final thing. There's a recent observation from this paper by Lian et al. 22, who used apogee to look at the age metallicity relation in the galaxy at different radii. So these different colored lines refer to different regions, radial regions of the disk. So this red and magenta line of the inner galaxy, you can see that as you get younger in stellar age, you get more metal rich. But as you move out towards solar neighborhood and a little bit beyond, like this orange and this kind of browny green color, you can see that at 8 gigayears, you get a drop in the metallicity of stellar populations, and it reaches a trough at about 6 gigayears ago, before increasing again at younger ages. And this is exactly what we would expect from this scenario when we get the accretion of this metal-poor, gas-rich small merger that we need to create this bimodality. So I think this is also very interesting evidence that may corroborate our little theory here. Okay, so that was essentially it, and this is my summary slide. So I just wanted to give you the main points, which were that the Gaia-Enceladus-Sausage object, the last significant merger of the galaxy, likely merged between 8 and 10 gigayears ago, created a dual origin for the thick disk by causing a starburst and heating the proto-galaxy material, and could also have incited bar formation if it were on the relatively light side of mergers in our simulation suite. And then for the formation of the chemical thin-thick disk dichotomy, it's this rather peculiar mechanism whereby we need a starburst at the beginning, then a shrinking gas disk from a lack of gas accretion, and then the reaccretion of a gas-rich minor merger at late times. Thanks very much for your attention.
Thanks a lot, Rob, for the very nice talk.